What specific problem does the new method aim to solve in the context of MLP activation dynamics in a transformer block?
The new method aims to solve the problem of understanding and analyzing the sparsity patterns and evolution of hidden unit activations in multi-layer perceptrons, MLPs, within a transformer block. Specifically, the method focuses on investigating how sparsity changes over the course of training on a per-token level and between tokens in a sequence or batch. It aims to address the issue of neuron death, where many hidden units are never used during training, particularly in the first layer of the network. The method also aims to explore how different layers in the network exhibit distinct sparsity behaviors, with some layers gaining neurons over training while others lose them. Additionally, the method seeks to examine the relationship between sparsity and model usable capacity, investigating whether the sparsity patterns observed reflect the effective utilization of model capacity. Overall, the new method aims to provide insights into the internal machinery of transformer MLPs and enhance our understanding of how these models learn and store information.
How does the proposed method of examining sparsity evolution over training differ from previous works?
The proposed method of examining sparsity evolution over training in this paper differs from previous works by focusing on the activation dynamics of two-layer MLPs in a standard transformer block, specifically looking at how sparsity evolves over training on a per-token level and between tokens in a sequence or batch. This work goes beyond previous studies by not only analyzing the extent of sparsity and its evolution patterns based on layer index, but also by exploring how sparsity patterns at the token, sequence, and batch levels frequently anti-correlate. Additionally, this paper delves into the concept of neuron death and how it varies by layer during training, showcasing that some layers gain neurons while others lose them. The study also introduces the idea of feature specificity to explain sparsity behavior, illustrating how features shift from a continuous shared subspace to a binary representation as you move higher in the network. Furthermore, the paper investigates how sparsity relates to model usable capacity by examining the revealed preference of capacity and exploring the sensitivity of sparsity patterns to hyperparameters such as learning rate, hidden dimension, and model depth. Overall, this work provides a comprehensive and detailed analysis of sparsity evolution over training in transformer models, offering insights that go beyond what previous studies have explored.
What are the core metrics of sparsity defined and calculated in the paper?
The core metrics of sparsity defined and calculated in the paper are 1. Per token hidden unit use. This metric calculates the number of hidden units that are non-zero post-ReLU per token and then averages this value over a sequence and batch. 2. Per sequence hidden unit use. This metric determines the number of hidden units that are non-zero post-ReLU anywhere in a sequence. It considers if a hidden unit is used in at least one token in a sequence. 3. Per batch hidden unit use. This metric calculates the number of hidden units that are non-zero post-ReLU anywhere in a batch. It is similar to per sequence hidden unit use, but considers any token in any sequence in the batch. These metrics are calculated independently for each layer in the network and provide insights into the sparsity patterns at different levels, per token, per sequence, and per batch.
How does sparsity evolve over the course of training according to the findings presented in the paper?
According to the findings presented in the paper, sparsity evolves over the course of training in distinct patterns based on layer index. The first layer consistently uses the fewest hidden units in a batch, while the final layer uses the most. Sparsity patterns at the token, sequence, and batch levels frequently show anti-correlation, with some layers gaining neurons over training while others lose them. Neuron death, where hidden units are never used in a batch, varies by layer, with some layers experiencing more neuron death than others. Additionally, about 5% of hidden units are at or below zero for every token at initialization and never activate, suggesting potential for better optimization of ReLU transformers. Sparsity tends to decrease as peak learning rate decreases, and wider models generally exhibit higher levels of sparsity. The paper also explores how different hyperparameters, such as learning rate and model depth, impact sparsity patterns. Overall, the evolution of sparsity over training is complex and varies based on layer characteristics and training dynamics.
What are the primary limitations mentioned in the paper regarding the choice of model size and activation function?
The primary limitations mentioned in the paper regarding the choice of model size and activation function are that the focus on small models and ReLU activation functions pulls the conclusions further away from immediate applicability to modern foundation models. The constraint of focusing exclusively on small models was due to the amount of metric iteration and the number of ablations involved in the work, which would have been infeasible to justify with large models. The choice of ReLU activation functions was motivated by the fact that ReLUs induce hard sparsity, making it easier to study. The authors hope that future work can identify proposed changes to initialization functions or other aspects of model structure to allow for more effective use of capacity across both ReLU and more competitive activation functions.
Can you illustrate step by step how the proposed method analyzes the sparsity patterns at initialization and during training?
The proposed method analyzes sparsity patterns at initialization and during training in the following steps. 1. Sparsity at initialization. The method first examines the sparsity characteristics of an untrained model. It observes that higher layers of the network use progressively fewer dimensions at the start of training. This suggests that even a random network induces sparsity as inputs shift through successive layers. The analysis shows that hidden units that are initially unused can become active during training, with higher layers activating more hidden units. This indicates a shift in the distribution of outputs as information flows through the network. 2. Evolution of sparsity during training. The method tracks the evolution of sparsity during training by analyzing metrics such as the fraction of hidden units active per token and the median fraction of tokens using a hidden unit in a sequence. It notes that different layers exhibit distinct patterns of sparsity development. For example, the final layer initially shows a decrease in hidden unit usage, while layer 0 gradually increases the frequency of using its hidden units over a sequence. 3. Determining neuron death. The method investigates when a hidden unit can be considered dead by analyzing its activity over a batch. It introduces a test at 50,000 training steps to mask inactive hidden units, finding that the model's performance remains unaffected. This suggests that unused hidden units early in training may not be essential for model performance, indicating a potential for reshaping the model to exclude such dimensions. 4. Understanding neuron deactivation. The method challenges the conventional view of neuron death as a random or accidental process. It argues that inactive hidden units within a batch can be reactivated during training, indicating a more structured process of sparsity emergence, driven by the model's construction of feature spaces. The analysis shows a nonlinear increase in hidden units being turned off after an initial stabilization period, suggesting a deliberate rather than accidental mechanism behind sparsity development. By following these steps, the proposed method provides a detailed understanding of how sparsity patterns manifest both at the initialization stage and evolve throughout the training process in deep networks, specifically focusing on the activation dynamics of MLPs in transformer blocks.